Let's start with an exterior test carried out on a rooftop in an industrial area of Hiroshima in Japan. FEVE and polyurethane coating samples were exposed for 15 years. A portion of each panel was masked over to prevent degradation of the coatings over time and to provide baseline measurements for comparison with the weathered coatings. Photo micrographs of cross-sections from each coating can be seen above. These two pictures show a cross-section of a paint film that's been applied. The layer of white is a layer of top coat. On the left-hand side, we have the FEVE top coat of 50 microns. On the right-hand side, we have a polyurethane top coat of 75 microns. And then half of these top coats has been masked off, leaving a small section exposed to the natural elements. The photos show that about 1/3 of the polyurethane's original thickness of 75 microns has been lost to degradation. Although coating remains, the appearance of the coating would be poor compared to its initial condition. In contrast, the FEVE fluoropolymer top coat has lost very little of its initial thickness of about 50 microns. Losing an average of 0.07 microns per year means that the fluoropolymer top coat has a theoretical life exceeding 100 years. Earlier, we saw pictures of the Blackfriars Bridge and the Hammersmith Bridge. If you were to rub the surface with your hand, you get a dusty residue, chalking, which is the top coat actually deteriorating and eroding. The next slide really shows how a fluoropolymer top coat encapsulates everything underneath, and not only provides a better cosmetic finish, but also protects the underlayers. On the left-hand side, when exposed to UV light, the top coat is remaining intact, thus protecting the underlying epoxy primer and intermediate coat. On the right, however, with the traditional polyurethane top coat, as the UV finally breaks through the surface, it will then attack the primers, and the primers have very limited UV resistance. This will finally end up with corrosion initiation of the substrate, and the coating system becomes virtually defunct. Simply upgrading the top coat to a fluoropolymer top coat will greatly enhance the longevity and performance of the paint system. Now, let us look at some laboratory-based accelerated testing. This slide shows at the top a salt spray chamber and below a QUV accelerated weathering chamber for testing gloss and color retention and UV stability. In a typical salt spray test, a standardized solution of 5% NaCl, sodium chloride, is used to create a highly corrosive atmosphere. Further environmental conditions such as temperature and humidity are controlled, and results give accelerated data on how coatings would otherwise perform over many years' exposure. To simulate outdoor weathering, the QUV accelerated tester exposes materials to alternating cycles of UV light and moisture at controlled, elevated temperatures. It simulates the effects of sunlight using special fluorescent UV lamps. It simulates dew and rain with condensing humidity and/or water spray. Typically, painted samples are exposed to a cycle of 4 hours of UV, 4 hours of humidity, and then 4 hours drying, over and over again for thousands of hours. Results show fluoropolymer coatings provided a far better long-term resistance to UV than existing traditional coatings. Results of another specific 5,000-hour test are also interesting. These results are taken from a QUV chamber, using QUV UVB exposure. It's important to understand what this means. Ultraviolet light spans a large area of the electromagnetic spectrum, from visible light down to X-rays, and is divided into A, B and C. 95% of the UV and sunlight that reaches the Earth's surface is in the A band, and only about 5% in the B band. Fortunately, no C band penetrates the Earth's atmosphere. This test was done using B-band UV light only, and so is a very harsh test and is more severe than everyday UV exposure in the field. In this screen, you'll see a blue line which is FEVE compared with polyurethane, the orange line, and then polysiloxane. You can see from the chart at the bottom that over the 5,000 hours the percentage of the gloss of the Vitriflon FEVE has gone from 72 down to 37. So there has been a reduction, but nothing when you compare it with polyurethane, where it's gone from 67 down to 1.3, and the polysiloxane from 69 down to 1.2. The test also showed a gloss retention of 52% on the FEVE and a colour variation at 8.8, measured in delta E. At 8.8, it shows a shift from the original colour, but nothing compared with the others. In polyurethane, the gloss retention is at 1.8% and the colour variation nearly 20%. While the polysiloxane showed marginal improvement, but still doesn't compare with the performance of the FEVE. This is what the panels look like when they come out of the QUV chamber, making the effects of the UV exposure very evident. You can see the aperture of the small window there that's been exposed, and the panel on the left showing the superiority of the FEVE technology.